Good morning. So, a brief summary of the first lecture. In this part of the blackboard, I will, during the discussion on the supersymmetry of the action, I will put the gamma identities that we will need for the calculations and also the fields identities. Actually, there is only one fields identity that I will write down here, and it will be the only identity we will need throughout the discussion. We started by considering the Lagrangian, and this Lagrangian of supergravity we have written first in components, in coordinates, without using forms. I will rewrite it here. Actually, it is the action. And, well, there is Newton's constant if you want to be precise. And then we saw that in our geometrical formulation, what comes out is the scalar curvature times the square root of the determinant of the metric minus, and then there was a constant a that we have not fixed yet, and then you had the Radita-Schwinger action, where here we put a covariant derivative on the Gravitino field and putting indices everywhere, because now I'm doing it in the okay, and this, everything here, is multiplied by the volume element. Now you notice that here you have square root of minus g times p for x, which is the invariant volume element. Here you do not need a square root of g, because this is already a scalar density of weight minus 1. It is scalar density of weight 1, and so this is indeed a good tensor. So this is the action we wrote down in the component formalism. And now what I want to use are really forms in order to get rid of these indices, most of them, all the curved indices. Now, for this, I will briefly recall some notations in differential geometry that we will use. There are some tools that I discussed, giving them for granted yesterday, and today I would like just to list what are the tools that we have used, and I will put them here. Some tools in differential geometry. Okay. Well, differential manifold or a manifold is something that will be very intuitive and not rigorous at all, that looks more or less like Euclidean. Looks like Euclidean space, Rn, around each point. So, for example, a line or a circle is okay because around each point it's more or less like R1. This is not a manifold because around this point it doesn't look like R1. These are examples of manifolds and things that are not manifolds. But being able to assimilate a manifold locally to Rn means that indeed there is a map, and this is the coordinate map. As you know, if you have a manifold, then you have a neighborhood of a point, and this you can map into Rn. This map, you can call it phi, and it identifies every point here, it brings any point here in a point in Rn, and the coordinates of this point of Rn are called the coordinate system of this manifold in this neighborhood. So this phi is also called the coordinate map. Now these maps have to be continuous and bijective, so they are homeomorphisms. Not only this, you can choose more than one coordinate system. You can choose another map from another neighborhood which has a non-null intersection with the first neighborhood. Here you have another map that you can call psi. What now you require is that the transition functions between this region and this region are actually diffeomorphisms, continuously derivable infinitely many times. And this map is simply psi minus 1 composed with phi, right? Takes a point here and brings it here towards this map. And this is the so-called transition function. So more or less these requirements of infinite continuity in derivation of these maps are what technically define a differential manifold. This being said, very quickly, we want to generalize the notion of a vector in Euclidean space. To a vector, well, I'm saying Euclidean, it can be pseudo-Euclidean, I mean, it is just Rn. A vector in Euclidean space, now you know that you cannot just see it as an arrow in a curved manifold, a general curved manifold, but what you can generalize from Euclidean space to an arbitrary differential manifold is the notion of directional derivative. This can be generalized. As you know, the directional derivative you can write as a gradient along some vector of a function. This is what in components you write like this, and this is the directional derivative in a Euclidean space along the vector V. Now this you can generalize to an arbitrary manifold by identifying this vector, this Euclidean vector here, with, in fact, a vector that will be an operator on the manifold, on functions, and this operator operates in this way, is defined as v mu d mu, acting at the point of coordinates x1, xn. This p is a point on the manifold that has these coordinates. P is a point on the manifold, that has x1, x2, xn coordinates via the coordinate map. This thing here is perfectly defined on any manifold. So you see, I'm now transferring the notion of vector on an arbitrary differentiable manifold as a directional derivative. So it will be an operator, and this operates on functions of x1, xn. This thing operates on these functions. These are partial derivatives. These are coordinates in general from a coordinate map on your manifold. So this is how we will consider vectors. The tangent vector, we will call this a tangent vector at point P of the manifold. Now, as you see, it's clear that these coordinates of the tangent vector depend on the coordinate map, because if you change coordinates, this changes as the Jacobian of the transformation, and these must change in the contra-gradient way. Okay, now the basis of this tangent vector, as you see, is simply given by the partial derivative, this you can see as a basis of the tangent vectors. The set of all tangent vectors is called the tangent space at P. The set of all these tangent vectors is called the tangent space at V, and the tangent space at V has a symbol. It is T of M at P. This is the symbol that labels the tangent space, the vector space, of all the tangent vectors at the point P of the node. Now, this can become a field, a tangent vector field, if you allow here this V that started as constant coordinates, you allow them to be dependent on the point, and so this will be a tangent vector field in the sense that in every point of the manifold you will have this object defined, so it becomes P of x. Well, I don't put P anymore because it refers to any point x of the manifold now as V mu x d mu. And these derivatives now are done at point x, the generic point x. Here they were done at the precise point P. Let's see. This is what I call a vector field on my manifold. Okay. Having introduced vectors, now I introduce forms. As you said, going quite quickly through this thing. And I will introduce forms as the objects that are in fact dual to vectors. Dual in the duality sense of vector spaces also. And I will start immediately with an example. I will introduce one force on M. One force on M are defined as linear functionals on vectors. Linear functionals on these vectors. Remind you that the basis for these tangent vectors is given by the partial derivatives. Example of a linear functional on vectors, it will be indeed the differential of a function f. Differential of a function, this is a function of these coordinates. The exterior derivative of this function, I call it differential of function, and it is defined in this way. I have to tell you how it acts on any vector at point P, and it acts in this way. It acts applying the vector P to the function f simply, which means d mu df over dx mu at point P. Of course, you can take out the P and put here the next dependence if you are defining it on the whole manifold, which we usually do in fact. In particular, okay, so I defined you a linear functional. Why it is linear? Because this is a linear operator and so on. And it is a functional because it brings you a vector into a number, into R. This is the definition of the exterior derivative of a function acting, since it is a one form, acting on a vector. Now, in particular, you can choose f to be the coordinate function. This is a particular function. It is a function of the coordinates, and then I choose really one of the coordinates. If you choose this, then you see that the differential of this function is differential of the coordinate x nu acts on any vector, I'm not putting the P anymore, I'm considering vector fields really, on any vector in, according to this definition, in this way. Well, yes. This is really dx nu, and here you have the vector that I wrote as mu. And now, the definition of this is the derivative here acting on the function that is this one, and you see what is the result. The result is simply v nu, because it would be derivative with respect to mu of the coordinate x nu, which is a delta mu nu, and the delta mu nu transforms this index into nu index. In particular, indeed, we found then that dx nu on d nu is the delta mu nu. Right? By definition of how this one form acts on this. It acts like the derivative of this on the coordinate x nu. So you see that if this was a basis for tangent vectors, this is a dual basis for one forms. Is a dual basis, and I can use this basis, the differential of the coordinates, as a basis of one form on the manifold. A generic one form omega, I can expand on this basis always, and it will be expanded like this, mu dx mu. And I say that I have the components of the one form on the coordinate basis. The space of all one forms has a name, and it is called the cotangent space. The cotangent space at P, if I'm considering everything at point P, it is called the cotangent space at P, at point P, or generically at point X. The cotangent space of M, of the manifold M, at point P. And it has a symbol also, which is T star. Like this. This you find in the books of differential geometry. At point P, and then of course it can depend on X, and it becomes a one-form field on the whole manifold. Fine. Okay, this one-form field then has transformation properties if you change the coordinate map, but these I will not write them down, they are well known. The dx mu changes as a differential, changes under general coordinate transformation, and this changes in the contragradient way, in such a way that this remains unchanged. And the notion of forms and vectors is an intrinsic notion that does not depend on the coordinate system. It will be written like this in any coordinate system, provided indeed that you apply the correct transformation rules that are contragradient one to each other in order to compensate the transformation. But it is done with the matrix, this matrix that is done with the derivatives of the new coordinates with respect to the old coordinates. But this I will not go into, since it is. Now, on M, you can, as we have defined vectors and forms, you can define in general tensors that will have R covariant and S contravariant indices in the usual way, that is, you start with a mu1, mu r, s1, then mu1, mu s, and here you put And here you put, well, in the coordinate basis, you have this d mu1 tensor products. You have to remember that these are functionals, so you can act, you can form tensor products of these things up to mu r, and then you tensor it with differentials of the coordinates dx mu1, dx mu s. And this you call a tensor with r contravariant indices and mu covariant indices. And again, the transformation properties of partial derivatives and differential tell you how these components transform. This is not equal. This is component on this basis. Everything is clear. I mean, it relates to things that are well known, but I will need some notations. Right? It is clear also why the differential transforms contract gradiently with respect to the partial derivative. The partial derivative, you know very well how it transforms. This has to transform in such a way to maintain the duality relation dx mu d mu equal delta mu, and to maintain it, then this has to transform as a differential, as we know. Okay. Again, if you put here an x, it depends on x, and you have a tensor field on the manifold. Now, once you have one forms, you can have p forms by multiplying them, but we multiply them in an antisymmetric way, and this is called the exterior product. And the definition is this. The exterior products of two basis elements of the space of one forms is defined in this way. It's defined as 1/2, and then you have dx mu tensor product dx nu minus dx nu tensor product dx mu. This is the definition of these exterior products. Here, this is a tensor products of functionals on tangent vectors, which means that this object acts on tangent products of say tensor products of vectors. For example, it acts on the tensor product of these two basis vectors in this way. This gives you a delta mu x on this, mu rho, delta mu x on this, mu sigma, right? So you have to see tensor products of one form acting on tensor products of vectors. This is how it acts. And this is how this is defined. So if here I put a wedge product, then this will be a two form. It will belong to the tensor product of two one forms that will act on these basis elements of tensor products of vectors, not anymore in this way, but this is anti-symmetrized, as you see. So here it will be anti-symmetrized, and this will give simply then the anti-symmetrized delta that we have already introduced, which is this one. These exterior products can be generalized to p forms. You can put more of this dx, and here you will just anti-symmetrize on the whole set of these dx, right? With 3, then we'll have a x rho here. Here you will have 1/6, which means 3 factorial, and then here you sum all the permutations with their minus or plus sign according to the signature of the permutation. And this will be the exterior product. Okay. once we have defined this, I will use two more things and it will be it. It's all that I will use. The exterior derivative. This has been already defined. It is defined on forms, on P forms. A zero form is just a function. The one form you can expand on the dx mu basis and so on. Exterior derivative on P forms, we have already defined it on functions. Now I want to define it on any P form, P form, and then it is defined, and these I'm just recalling what we have defined. A P form can always be expanded in components as mu1, mu P dx mu1, exterior product dx mu pi, since this is the basis for P forms. And then this is defined as the exterior, as the partial derivative with respect to, let's say, well, I'll find an index now, omega pi components mu1 mu pi P. And then here I have dx mu1 dx mu P. And here I put an extra dx, which I call mu0, for example, and this I differentiate with respect to mu0, the coordinate x mu0. And this is the definition of exterior derivative of P form. You notice that this exterior derivative maps P forms into P plus 1 forms, because you added here the differential multiplied by exterior product on the P form you had before. So this is a P form, this is a P plus 1 form. Now, together with the exterior derivative, there is also an operation that lowers the degree of the form instead of increasing it. And this operation is called the contraction, and the contraction operation is defined as follows. Contraction on P forms is defined in this way. It is defined with the symbol I, and along a vector V. This vector is expressible on a basis, on a coordinate basis like this, and this acts on a P form as follows. It acts as follows, as P times, and then you have V mu contracted indeed with the first index of the omega mu, and then you have the mu1, mu2, mu n, dx mu2, dx mu n, and this is what is called the contraction. And as you see, the first index has been eaten up by this contraction with the components. Sorry?
P mu form till mu P, because you have P form.
Sorry, what is the
so the indices should be till mu P.
Mu
P.
here?
No.
The last index.
Mu P, you're right. Totally right. And so here you see there is a P minus 1 form, basis element, and so this is a P minus 1 form. So this decreases the degree of the P form by 1. Okay. Exterior derivative raises, contraction lowers. Then you may wonder, but then I can combine exterior derivative and contraction to construct an object that acts on P forms and leaves P forms in P forms and puts P forms in P forms. And in this object is called the Lie derivative, and it will be rather important because it will be indeed the technical tool we'll use to express transformation rules in supergravity theories when they are interpreted as diffeomorphisms, because the Lie derivative is what is really generating diffeomorphisms. And this we will prove because it is a rather important point. And the Lie derivative along the vector is defined as this operation. First you apply the contraction, and then you apply the exterior differential, and then you take the reverse order, and you act with this on any P form. And this is the action of the Lie derivative. This on a P form is this on the P form. The action of this and the action of this has been defined on P forms. So this is a well-defined object that we will examine later. Actually, even now. Finally, I have to tell you one line about integration, because this, after all, is an integral, and I want to define integrals on forms. Integration on P forms. Well, actually, I will take n forms, where n is the dimension of the manifold I'm integrating on. And so I will have n integration, and I have to define to you what is this thing, the integral of an n form on an n-dimensional manifold. And this is defined to be this, to be omega mu1 mu n, since this is an n form. And here you would have dx mu1 dx mu n. And this, I define this integral of this P form, of this n form on an n-dimensional manifold to be exactly this, omega mu1 mu n times epsilon symbol, the Levi-Civita symbol mu1 mu n. I contract all the indices, antisymmetric indices of the form with the antisymmetric indices of the Levi-Civita. So it is the sum of all components with their permutation sign in the end xn. And this is the usual volume element on Mn. Well, it is not the invariant volume element. It is really dx1, dx2, dxn. The one that one uses in a coordinate system just by multiplying the differentials. It is not the invariant volume element. It is the one that you learn in calculus. This is defined, and now, is this a good definition of integral? Yes, because this and this transform with inverse weights, so that under general coordinate transformations, indeed, this is a good volume element. Because again, the Levi-Civita tensor is not transforms, it is not a tensor, but it is a tensor density. It transforms with the determinant of the metric, not of the Jacobian of the transformation, if you change coordinate system. So this is why we are using 4 forms when we rewrite these in the language of forms, because we want to integrate these Lagrangian on a 4-dimensional manifold, since we are speaking of supergravity in 4 dimensions. When I will generalize supergravity to higher dimensions, then we will have P-form Lagrangians, where P is the dimension you want to construct your theory on. In particular, in 11 dimension, we have an 11 form.
What if you want to integrate over a form that is in the top form?
Then, well, this is only defined if you integrate on a manifold that has the same dimension of the degree of the form. which is fine. I mean, you can integrate this. Suppose your ambient space is an n, you can consider a P form with P less than n, and you can integrate it on a submanifold of this manifold.
Okay.
P-dimensional submanifold of the manifold that encloses everything. In fact, these things have all the properties you know about area elements or hypervolume elements. They have exactly the same properties. If you look at the transformation properties, you will find that it transforms exactly with the determinants that you find in usual area elements and so forth. And this is actually why forms are useful. And this I would like to conclude with only the Stokes theorem that can be formulated very compactly in the language of forms. It tells you simply this, that if you integrate on a manifold M form that is exact, I call exact the form that can be written as the differential, as the exterior derivative of a form of degree p minus 1, if this has dimension p, you see then this has dimension p, and I can integrate it on a manifold of dimension p. This, by Stokes' theorem, is equal to the integral on the boundary of this manifold. The boundary of this manifold has dimension p minus 1, since it is the boundary, and here you can put omega p minus 1. And this is Stokes' theorem. That takes various forms that you have learned. For example, if the ambient space is n equal 3, then you have Gauss' theorem and so on. But this is it. And this will be used to integrate by parts. You will be able to discard total derivatives in the Lagrangian written in the form language only if the boundary of the manifold is trivial, or if you have suitable boundary conditions for the fields. If the boundary is at infinity and the fields are 0 at infinity, even if the boundary is non-trivial, you can integrate by parts because you will have no boundary terms. This is the boundary term. Okay. Since we are here, I will convince you that the Lie derivative indeed generates a diffeomorphism, so that we have it out of the way. One forms. Okay, so I have to show now what happens when you take a form in a point of the manifold x plus delta x, and you subtract it by this, and this will be the variation of the form. This will be a P form, the variation of the form under coordinate change. This is what you define as a diffeomorphism, change of coordinate, infinitesimal change of coordinate. You compare form in point x plus dx with the form in point x, and you take the difference. This variation, now, well, I can write it this way, omega mu. It is the variation of the form, omega mu x, times x mu, under infinitesimal coordinate change. And now here, I will vary the thing. Then x plus dx minus x, if I do the variation, it will be the derivative, partial derivative of omega mu times the increment of the coordinate. First order Taylor expansion. This is it. This is the variation of omega times dx mu. And I did the variation of this But now I must vary the differential under coordinate change, and this also varies, plus omega mu of x, but I'm not putting the x dependence anymore, d nu, and here dx mu, dx nu, right? Because that is what it is. It is, this enters here, and it is the exterior derivative of the variation, but the exterior derivative of the variation, I expand on a one-form basis, and it will be d nu dx nu of the variation. So I'm just writing the exterior derivative on the coordinate basis of one form. This is it. Is equal. Is it clear, the logic? Here I can factorize the dx nu. Here you have a dx mu, but I rename this index nu, dx nu, and then if you rename correctly the indices, this gives you this, omega mu minus plus d mu omega mu dx mu. I have just rewritten terms and factorized x dx mu. Okay, now I rewrite this in a more suggestive way, in this way, d nu. Here I take this, but I take the dx nu of dx mu, this whole thing, omega mu, plus then d nu omega nu, and then I have to subtract what I put here, because here I put this also on this, which was too much with respect to this, so I subtracted here d nu omega nu. And here I have dx mu. I just rewrote the thing that was above. Right? Because you have this term, and this term was this here, but then here you have also this term if you act here, and I subtract it here. So you reconstruct here a curve. And this, finally, is equal to the exterior derivative of dx mu omega mu plus. And this, you see, these are just the components of what I call the exterior derivative of these one forms, components mu nu. Components mu nu of the exterior derivative of one form are really this curve, so I call them like this. And then they are multiplied by dx mu, dx mu.
Sorry, in the preceding line, I'm confused on where the delta and the d is. So in the
sorry?
So I'm confused of where the delta and the d is already in the second line.
The second line is this
the
one.
First term, who has the delta on the first term?
The d is variation.
Sorry?
This should be, second d should be current d.
You are right.
This one should be really, okay.
Yes, this was this.
Okay.
You're right. This is a variation, yes.
Because, okay. But I thought I see. Because the non-curly one is always contracted with the omega. No? I mean, already in the first line.
The first line, these are contracted, yes. Everything is contracted. Did I write something wrong?
This is second.
So the second term makes sense there, but the
No,
first,
but you wrote second term first.
yeah, that's fine.
Yes.
But
This is this one.
I mean, for example, the first term then you have.
This is this one,
No,
but
you
I
changed
interchanged
Ah.
summations because, okay.
Okay, sorry, yeah, okay, yeah.
New in such a way to
Yeah,
factorize
okay,
this.
yeah.
Okay, at the end you have this, but this you can rewrite as exterior derivative of the contraction on this vector here is a vector field that I write as d mu in this way. It's a vector because I write it in this way on omega plus the contraction along this vector of d omega. This is the final formula because this indeed, you see, is how I define the contraction on one form. It's really the contraction of the vector field with the only index of the one form. So this is it. And here you have the contraction of this, because you see that this, by definition, is really the components mu times the basis element. And if you contract it along this vector, you have to contract this, you see it disappears. You have to put a factor of 2 because you have a factor of 2 here when it is a 2 form. And this is a 2 form, and so you put a factor of 2, and this factor of 2 is the one you have here. Okay, the upshot of this is that you have rewritten this variation as the Lie derivative along this vector here. This is a vector because I write it like this, of omega. So the diffeomorphism on a P form is expressive, yes?
So that's the derivative should be a plus.
Where?
The definition of the derivative.
The definition of Lie derivative should be a plus, sorry. Yes. You are totally right. I don't know why I put the minus. The definition should be a plus. In fact, by doing it, we checked that it was a plus. Okay, that will be all about our very quick review of notations in differential calculus. And this proof I wanted to give because it will be an essential tool. The derivative along the vector is an essential tool in our consideration. Here there is a delta omega. So there are questions about this recapitulation? All of these you can find on textbooks, like for example Diagucci-Anson physics reports on differential geometry for physics, with many examples. Now I'm just skipping most of
The derivative along delta x.
Sorry? Did I...
The derivative along delta x.
The variation of omega is by the Lie derivative along delta x rather than delta.
Yes, along delta x. Okay, so we can come back to supergravity, and then you will allow me now to transform this integral in an integral on a 4 form, and it is indeed what we started with yesterday. I have already proven to you that the first term you could rewrite as an integral over, now I'm forgetting the Newton's constant in front of everything, as an integral over RAB, exterior product BC, exterior product BD, times the epsilon symbol with Lorentz indices, where RAB was defined as this expression given in terms of the spin connection. Here I'm contracting indices with the Lorentz metric. And this field here being the Filbine field one form of the manifold. This is a two form because omega is a one form. Omega is a one form. V is a one form, so these are the objects that I have in usual general relativity in first order formalism. The field bind one form and the spin connection one form. This is an exterior derivative of the one form, so it will be a two form. Here you have exterior products of two one forms, so this is a two form, this is a two form. My conventions have a minus sign here. So I have defined what is this, and we saw yesterday, just by expanding on a field bind basis, that it reduces to this term here, times the invariant volume element, which is minus G times d4x. Now, the same can be done here, using sigma, and in fact, it will be minus A. And here, this thing I can write, and you see that this is quicker to write, it's this, gamma A, D as an exterior covariant derivative, psi, dA. Now here I should put everywhere, I have forms, I should put everywhere an exterior product. But now I'm taking the convention that whenever I multiply forms, I multiply them by an exterior product, so that I don't have to put these wedges symbols everywhere. This is a four form. This is a four form, 1, 2, 3, 4, four form, and I can integrate this on a four-dimensional manifold. If you expand this on the dx mu basis, you reconstruct this epsilon mu rho sigma d4x. Okay. Now, we have to prove that this action is supersymmetric, and this is what we start to do now. We'll just begin to write down what are the transformation rules under supersymmetry that I want to see whether the action is invariant under. And here I do it. So now we are looking at supersymmetry. Local supersymmetry, which, contrary to what has been discussed by Ferretti now, will involve a x-dependent parameter. Now, the rules that we will propose to try them against this action will be the variation of the gravitino. If I put even an index, you remember that there was a symmetry, a local symmetry of the Gravita-Schwinger action that looked like this with an ordinary partial derivative here. Now, since we are coupling it to gravity, I try the same thing but with a covariant derivative of the parameter. This is a spinor, spin 1/2 field, and this is the gravitino. The covariant derivative being defined, as we already said, by -1/4 omega AB mu gamma AB on epsilon. This is the definition of the covariant derivative. The whole thing can be rewritten without index mu, simply taking it as the variation of the form psi, and then this will be the exterior derivative of this, that is a function, a spinor function, and the exterior derivative of the spinor function is really exterior derivative on epsilon minus a fourth, omega, I take away this index, so the one form gamma is the epsilon. Well, this contraction is here, gamma is the epsilon. So now I'll take always forms, so I'm not putting components anymore. So this is the proposed variation for the gravitino field under supersymmetry. Then I have to propose a variation also of the Filbine field. Now here you can reason with dimensional considerations. There are not many possibilities. The simplest possibility is really something proportional to, this will be a constant that I will determine later in order to have invariance of the action. And epsilon bar gamma A psi will be my proposal. In fact, this proposal comes out of dimensional consideration. Because you can give length dimension to all the fields, taking in mind that the action should be a pure number when h bar is equal to 1. And then you see that, well, the covariant derivative has length dimension -1, obviously, since it is a derivative d over dx. The Filbine has length dimension 0, and the gravitino field has length dimension -1/2. If you take them as forms, since you are taking away this index, you are really adding a length dimension because you are adding dx mu, and so this as an exterior derivative has length dimension 0, v has length dimension, you have to add 1, so 1, and psi has length dimension 1/2. Psi has length dimension 1/2. So you see, if then this thing indeed has length dimension 0, because here you have the Newton's constant that has length dimension 1, and this has length dimension L -2. You can check that this thing has length dimension 0. Right? This has length dimension. Okay. Then, if you apply this reasoning here, you see that this, since this has length dimension 0, this has length dimension -1/2. This, what did I say? This is 1/2. This is 0, so this has to be length dimension 1/2. So here you have 1/2, here you have 1/2, and here you have 1. So this is the rule where the length dimensions are balanced, and it is in fact the simplest rule you can find. It has to contain epsilon, it has to contain psi because supersymmetry rotates bosonic fields into Fermi fields. It has to have an index, a Lorentz index. This is the only way you can combine it. At least it is the simplest way.
So is this constant the same as what we have in action? Or?
No, this is different. This is an A and this is an alpha. In fact, this A is fixed to 4. But this is an inessential constant because it really defines you the normalization of the psi field. So I take it to 4, equal to 4 for aesthetical reason. This is really not important. What is important, once you have fixed this, then this alpha is not fixed, is not free anymore, and it has to have a definite value for the supersymmetry to hold. Okay. One more thing, and then we can take a break. One more thing is related to the third field that you have in the game. Here you have a third field, which is the spin connection. Now, the spin connection could vary. But we remember that there was an equation that we did not finish to examine, the torsion equation. The equation of motion that you have by requiring that the variation of this action with respect to omega b is 0, right? This is the field equation you obtain by the variational principle when you vary the field, the spin connection field. Now we suppose that indeed this field equation holds. That is, then now we are assuming that we are in second order formalism. From this field equation, what we find, but I still have to prove it until the end, that omega can be re-expressed in terms of V and psi. Now, in the next hour, at the beginning, I will really show you what is this precise expression. But this comes out of requiring this field equation. Then, you see, if we are in this framework, in second order formalism, then this variation here is totally irrelevant. I can put it even to 0. Why? Because when I vary the action with respect to supersymmetry transformations, well, the action, it will be the variation of the action with respect to the fields, for example, to the field-bound field, times the variation of the field-bound field under supersymmetry transformation, plus the variation of the action with respect to the gravitino field times the variation of the gravitino field under supersymmetry transformation using the chain rule, plus you have the third term, ds over d omega ab mu mu times the variation under supersymmetry transformation of omega mu ab. But if I am in second order formalism, this has been taken to 0. This equation holds because I'm rewriting omega in this way, and if I rewrite omega in this way, this term is identically equal to 0. So you see, the variation of omega is not relevant to compute the variation of the action under supersymmetry. So I can totally disregard the variation of omega. I'm not varying omega. I could vary omega by what I want, and this will not influence, in any case, this thing in first order formalism, in second order formalism. So I can as well put it equal to 0. This procedure is also what is called, has been called by Peter van Nieuwenhuizen, the 1.5 order formalism. Since it is in the middle of the way between first order and second order formalism, it is first order because I'm still considering these fields to assemble together into this package that I call omega. But omega I only see as a package, a particular combination of V and psi fields. This particular combination of V and psi fields, I'm not transforming. I'm not transforming because I know that indeed it would not contribute. But I'm really in second order formalism because omega is not an independent field. But I'm treating it as a package, and this is why there is still a suggestion of first order formalism in the game, and the whole thing is called 1.5 order form. So now our goal will be to show that these rules, indeed applied to this action, will be a symmetry of the action, and for the action, for these rules to be a symmetry, we have to choose this alpha, and I tell you already the answer. This alpha will be set equal to I. If you set this alpha equal to I, this A equal to 4, this action is invariant under this transformation rules. Okay, so let's take a break. Okay, now I remind you that I still have to give this explicit formula for omega when I assume this equation to hold. And this is what I do here. Missing pieces, yes. Okay. So we wrote down, in fact, the variation of this Lagrangian when I vary the spin connection. This depends on the spin connection, and we saw that this would give the variation. Well, we already wrote down the formula, and the formula was the following. There were 2 times covariant derivative on d, c, because here I have an integration by parts, covariant derivative of the delta omega, transfer it here, integration by parts, and I have a covariant derivative of vc times vd, it is epsilon on this times dt, and then I have this epsilon abcd, and this was the first piece, the variation of the first piece with a factor of 2 because the covariant derivative hits this and then hits this. And then I have a minus. And here, the omega is contained in the term minus 1/4 omega ab gamma ab, the connection part of the covariant derivative, and so this gives a minus, because I put this omega in front to factorize it, a minus a4 psi dagger gamma phi gamma d. I don't know why I called it d. Ah yes, gamma ab because these are indices ab psi vd, and everything has to be put in here. This is the equation that comes out by imposing that the variation is 0 with respect to the spin connection. Is it clear to everybody? I remind to you that P forms and Q forms, this is a P form and this is a Q form, you can interchange them, but then you get a sign that depends on P and Q. If they are odd forms, then you get a minus sign. If they are not both odd forms, you get a plus sign. So you can put it minus 1 P times Q, omega Q, omega P. Okay? This is the formula for the commutation of form. If one of these two is even, then the whole thing is even and gives you a plus sign. This is why here I get a minus sign. Even if here I had a minus sign, it should compensate this, become a plus. But then the omega was in this position, and the omega to be factorized in front must come to this position, and then it has to jump over one form, and then it gets an extra minus. This one was already in the first position. And then I can factorize the d omega. I can put that the variation is this, where this is a variation of the one form. This is arbitrary, so this must vanish. And this is the equation that I'm considering now. Okay, so let's look at this equation. Now, what I will use is the following identity. I said that gamma identities I would put here. And the gamma identity that I'm interested in is the following: gamma phi, gamma d, gamma ab, which is exactly this thing, is equal to 2 times, well, the fact that there is a gamma phi is really irrelevant, the delta, and then I have a d, a, so this is an eta, for the Minkowski metric, gamma b. And then I have a plus I epsilon A, B, C, D, gamma C. Okay? This is a formula that you can check. All these formulas can be checked, and they all originate from simply the basic algebraic identity of the Clifford algebra. They all originate from this. And then, if I use that formula there, and of course the gamma 5 we have defined as I, gamma 0, gamma 1, gamma 2, gamma 3. I have to give you also the definition of the gamma 5. In this case, if you take the square of the gamma 5, which is the thing that you will have to use, you will find 1. So my normalization are gamma 5 squared equal to 1. Okay, this said, then we will remember the supersymmetry relations. They are very easy to remember, so I can cancel them. This said, I can substitute it here. So I have 2 derivative of field bind dB epsilon EBCD, and then I have minus A over 4 psi dagger, psi bar, and then I have I epsilon A B C D gamma C psi times VD times VD times VD epsilon A B C D. Is that correct? Because I just substituted in this formula this term here. And I substituted this term, but I forgot this term here. This term here. There is a reason why I forgot it, because you see, here you have a sandwich between psi and psi, psi bar and psi. Now the only matrices that
There are 2 epsilon ABCDs.
there are 2 epsilon that are too many, yes. Okay, I factorized the epsilon ABCD for both of them here. Yes. And now I recall that the only bilinear combinations with the same Majorana 1 form that can survive are those which have inside the gamma A or inside the gamma AB. Why is that? All the other gamma matrices in the Dirac basis, the other would be a gamma A, gamma 5, or gamma 5, gamma A, then gamma 5, and then 1. These are the 16 Dirac gamma matrices, the Dirac basis. Now, what I'm saying is that when I have 1 forms like this, then the only bilinears you can form are these 2. This is different from 0, this is different from 0. All the others are 0. Why? Because you see, this you can rewrite in this way. C alpha, charge conjugation matrix alpha beta, psi beta. Well, then here you have, I can write it like this, charge conjugation matrix times gamma A alpha beta, psi beta, right? Writing explicitly the spinor indices and reminding that psi bar, if it is a Majorana spinor, is by definition of Majorana spinor equal to psi transpose charge conjugation matrix. So psi transpose charge conjugation matrix times the gamma A, then these are the contractions, and here you have psi B. Okay. Now you see, since psi A and psi alpha and psi beta really commute between themselves because they are fermions and then if I exchange them, being Grassmann objects, you would get a minus sign. But they are also one-fourths, and they get an extra minus sign because they are one-fourths. And so psi alpha, psi beta is equal to psi beta, psi alpha. The fact that they are one-fourths compensates the fact that they are Grassmann numbers. So inside here can survive only matrices that are symmetric. Gamma matrices that multiplied by C are symmetric. Now, it turns out that in our list, we have that C gamma A is symmetric, and C gamma AB is symmetric. This is, again, just an output of the definition of the C matrix that is such that gamma A transposed is equal to C gamma A C minus 1 with a minus sign, and the fact that C squared is equal to minus 1. And you have, well, I'm putting just all the properties of the C matrix. If you use these properties, then you will find that the only matrices that are C symmetric, that is, when multiplied by C are symmetric, are the 1 index gamma and the 2 index gamma. C gamma 5, C times the identity, and C times A gamma 5 are anti-symmetric. Being anti-symmetric, they cannot stay here because this thing is symmetric. So it vanishes. So the only combinations where psi is a one-form Majorana field are C gamma A and C gamma AB. Okay, then you understand why I can forget this piece, because this piece had the gamma 5 gamma B, but the gamma 5 gamma B is anti-symmetric, and it cannot stay here inside. Whereas this piece here has only a gamma C, and the gamma C can stay inside, and this is where I put it, in fact. I put the gamma C here. So the only contribution is this. Okay. So this is it. Now here I can put, okay, minus sign. Let me see if everything is correct. Yes, sign. Yes. Okay. Now, at this stage, I can choose, I will choose A equal to 4. A equal to 4, just to simplify this 4. I mean, there is no other reason. And so, from now on, A divided by 4, and take it equal to 1. So this will be 4. The I put in front, I side by side. And here I have a minus sign. Okay. So this you can rewrite, if you wish, as 2 times RC VD RC VD epsilon ABCD equals 0, with R defined as derivative of VC, covariant derivative of VC, and minus I half psi bar gamma C psi. Correct? 2 times, it means 2 times this, 2 minus I, okay, this is it. And then you have the VD, okay? So this object here is what I will call the super torsion, but I don't want to call it the super torsion every time, I will call it just the torsion. I call it the torsion, and the equation that we just got here tells me that the torsion has to satisfy this. But we found already the solution of this, if you remember, in components. We saw that this equation had as solutions that RC as a 2 form, all the components of RC had to be 0. So I write it like this, RC really has to be 0. So this is the equation that comes out of varying the spin connection to the action. Okay, this equation I told you would furnish the deep side dependence of omega, and indeed it does. And now we check it. Okay. We already saw the solution of this equation, the explicit solution of this equation when this term was not present. And I will just then use this fact and remember it at the correct moment. So I write it, the covariant derivative of, let's put an index A here. So this RA is the covariant derivative of V, B, and then you have minus I half psi bar gamma h psi equal to 0. This is the equation you have to solve in order to find omega. Now, omega AB I can write as a sum of two pieces, the omega 0 AB, which is the omega that I find if this piece is not present. It is the omega given in terms of V that we found yesterday. Plus, there will be an extra piece that will contain linear inference that I call delta omega AB. Then you rewrite this formula simply as dVA minus omega 0 AB VB, okay, minus delta omega AB VB. This omega 0 plus delta omega is the omega you have here equals, and I bring this to the right, I have psi bar gamma x psi. This is the equation. And we have to find who is this animal, because this one we already found. Good, but now you remember that this is 0 by definition, because omega 0 was really the omega that solved this thing equal to 0. So this I can forget. You are left with an equation for the delta omega, the part that interests us. So the delta omega, I take a minus sign here, I put it here. The delta omega is given by this equation.
So how do you know that you can split the speed connection in that component?
I don't know. This is just a definition of who is this.
So why they don't mix? Because of spin. Side has spin 1 half, so you can't mix sides.
Look, this is just a definition. The omega AB, I decide to write as omega 0, which is a quantity that I know, plus something unknown that I have to determine.
But
That's it. I'm not doing anything more.
But you should solve the equation, not give a definition. And we have this solve. Yeah, the one that side it has spin 1 half, so you can't mix. Why we have it in solution psi times 0, for instance. But it is what the question.
No, you cannot have psi times V because it has to be bosonic.
Yeah, this is the thing. So you have it in mixed terms, so you can split it.
But look, I'm just renaming. This is an unknown quantity that I have to determine. I can name this unknown quantity something that I know plus something that I don't know. That's omega.
You'll have to do it even if it makes sense.
Even if it,
Yeah, even if you don't care about speed, you can't mix.
No, because the delta omega could be minus omega 0 plus
Yes.
other stuff.
yes, yes.
Yeah.
It just tells you that delta omega is this minus this. It is an identical. It's like when you do a change of variable in an equation. Okay. By the way, this is just one way. You could solve it also directly for this. I'm just doing it like this. But now this equation here, you recognize has exactly the same form of the equation we solved before for the torsion, and you solve it exactly by the same trick, by this trick here, by taking components and cycling over components, summing with plus, plus, minus signs. And indeed, what you find, you will do the same thing. This tells you that that delta omega AB mu V nu V. Well, this V is contracted with this with the metric. Now I don't want to put it downstairs. Equal to minus I half psi mu gamma A psi mu. Okay? Is I just extracted the form index mu nu mu nu. They are antisymmetric since they have two forms. And now here you do the same trick as we did before, and I tell you the result directly. This is the delta omega AB. You find. You just copy what we did for torsion 0 with bosons. Is I over 4. You find VA lambda VB nu. You have the two inverse field, the two field lines that multiply, and here we have the bilinears. And here we have the bilinears in the fermions. Psi bar mu gamma lambda psi mu plus you have the secret permutation gamma. I have mu lambda nu mu, and then with the minus sign, the final secret permutation, which is mu lambda. Okay. This is it. This is the solution for this delta omega. Well, not finished, minus lambda that goes into mu. This is the solution. Because, well, I could have put here in fact, I could have put here an antisymmetrization. So this is it. And it gives you a complete dependence on V and psi of omega. You have the first term, omega 0, that is given in terms of V, inverse V and derivative on V, and the second term, delta omega, that is given like this. Okay, now we are ready to go on with the supersymmetry invariance of the actions. Here it comes. Consuming chalks. Maybe I'm writing too much. Okay, so let's start. Variation of supersymmetry of the Lagrangian is equal to what? So I have 2 times. Now, this is not varying because it contains only omega, and we decided that omega I can forget the variation. So this is 2RAB, and then I have the variation of VC under supersymmetry, and this I can write immediately. The variation of VC this side was equal to alpha times epsilon bar gamma C psi psi, right? This was the variation of VC. Alpha epsilon bar gamma C psi. And I put it here, times VD times epsilon AB CD. Maybe with a factor 4, because this, and then I have this. So here there should be a 4. Ah no, because here there is nothing, so it is a 2. 2 is okay. Minus. Then we have to vary, so we have varied this and this. Now we have to vary this. So minus 4 times the variation of psi bar, well, the variation of psi is equal to covariant derivative of epsilon. So here we will have the covariant derivative on psi bar, on epsilon bar. Covariant derivative on epsilon bar. By the way, I should define for you who is the covariant derivative on epsilon bar. It is given by the epsilon bar plus 1/4 epsilon bar gamma AD omega AD. Notice the change of sign, the fact that the omega, the gamma acts from the right, since this is a transposed spin multiplied by the C-matrix. You can verify that this is the correct variation when you take the bar of this and the bar of this. Minus 4 and gamma phi gamma A, d psi dA is the rest that I have here, gamma phi gamma A, d psi dA. But I'm not finished, I have to vary this and I have to vary this. So I have 2 terms more, minus 4 psi bar gamma phi gamma A. And here I have gamma phi gamma A, the d of what? The d of the variation of psi. But the variation of psi is again a d, covariant d, so I have the square of the d on epsilon times v A. And the last term is the variation of this d there, minus 4 alpha, because the alpha comes out of the variation of v, psi bar, gamma phi gamma A, d psi, and then I have the variation of VA, which is epsilon bar, gamma A psi. This is it. This is the variation of the Lagrangian under supersymmetry. Now, let's work it out. We have eventually to prove that it is 0 for a judicious choice of alpha. Well, actually for alpha equal to I. Good. Now, let's use the following trick. The term with the epsilon bar, I can integrate by parts. And I tell you what it gives. If I take this, if I integrate it by parts, then this will come here and then here. So it will give you minus epsilon gamma phi gamma A. Here I get the minus sign because this is a 0 form. If I integrate by parts, I get the minus sign. D square of psi, dA, and then you have another term which will be epsilon bar gamma phi gamma A. You have the d psi, and then you have the dV, dVA, right? You just integrate it by parts. But now I remember that the dVA is, if you remember, it is the torsion RA, and I take out the psi bar gamma A psi term. So the dV you can rewrite as this. Since RA was equal to covariant derivative minus this, I can rewrite this. Okay? Now I'm working in second order formalism, so this torsion is zero, because the omega has been expressed in terms of V and psi. So this term here is zero, I'm left only with this. Okay. Okay. So this will be the only term that survives. Then I use it here. I replace this by two terms. I replace this by these two terms. There is a minus sign, so there will be a plus this. I take this away, and I rewrite plus epsilon. Well, there was a 4 epsilon bar gamma psi gamma A, d squared psi A, and then plus 2. Yes. There was a 4 divided by 2 makes 2. There is an I epsilon bar gamma phi gamma A deep C, and then there is this bilinear here, which is psi bar gamma A psi. Okay, I replaced the two terms, and then this is it. Okay, now observe the second and the fourth terms. These two terms contain a d squared. This is a d squared, this is a d squared. Now, you can compute who is the d squared, and you can guess that it will produce a curvature. D squared, after all, with exterior derivatives, is really commutator of covariant derivatives, and this produces a curvature. You can even compute it, who is the d squared on epsilon. You do it by just the definition of d. You repeat it 2 times, and you act on epsilon, and you will find that this is equal to minus 1/4 gamma Rs, and then you have epsilon. And then here you have Rs as a 2/4. So it acts with the same Lorentz generator gamma Rs. And the same holds for psi. The square of psi is the same thing, minus 1/4 Rs epsilon psi. Psi Rs. Okay, now you can use this. Oh, by the way, I forgot to tell you that the square of the exterior derivative is always 0, because it really reduces to a commutator of partial derivatives, which is 0. But the square of the covariant derivative is not 0 and is proportional to the curvature. Okay, now I'm inserting these inside here. Let's see if I can do it. Well, let's rewrite them. Maybe I can just insert them. Okay, so here I have minus epsilon gamma phi gamma E gamma Rs psi plus psi bar gamma phi gamma A. I'm just rewriting the second and the fourth terms. Rs epsilon, and everything multiplied by VA. there is an A here, gamma 5, gamma A.
Sorry, can I just ask a quick question?
Yes?
In the third term, you're very.
In the
So you've got
third,
the 2I epsilon gamma 5 gamma A B
yes,
psi.
yes,
Um,
epsilon bar, yes.
so then that's
This is linear.
okay, and that's coming because that's D of VA, is that right?
Yes,
That's
yes,
D of
this
VA.
would come from here.
Okay, sure.
This VA has two pieces, but this
Yeah.
piece is 0.
Thanks.
Here you had a 4, and then this is 6. Right. Now I'm writing this term and this term by using these formulas inside. So you see here you have a minus 1/4. Here you have a 4 and a 4. The 4 goes out, the minus stays, minus here, and you have a plus. So these are the two terms. And then you have the VA at the end of everything. The VA at the end of everything, here and here. Okay, now let's examine this term. This term, again, is a term where you have, you see, you have epsilon bar psi, psi bar epsilon, with a minus sign of difference. So here, it really means that the contributions of gamma A, gamma RS, gamma A, gamma RS, that I wrote somewhere here. No, I did not write them. So we'll write who is gamma A, gamma RS. Gamma A, gamma RS. In fact, you can deduce it from here. You multiply by gamma 5 here, multiply by gamma 5 here, and you multiply by gamma 5 here. And you have with the product of a gamma with one index with a gamma with two indices. So you see, gamma with one index times a gamma with two indices gives me gammas and gamma 5 gammas. Now here we have the same reasoning as before. The only thing that can contribute is the gamma 5 gamma C term. In fact, it will be this term that contributes, because if you put this term inside, you see that the gamma 5 goes out, it disappears, gamma 5 times gamma 5, and the only term that will contribute will be a gamma C, let's say. We will be left with one index gamma. And one index gamma is what you need in order for this thing to be different from 0. This thing with a sign difference can be different from 0 only if you have the gamma C part that is selected out, because these two things sum. These two things sum.
Sorry, which term is this that you're this?
Now, I'm using the gamma formula to substitute these, and in principle, I should substitute it with this plus this. What I'm saying is that this does not contribute in this case, because if you wrote this term, you would have a single gamma instead of this product of two gammas, but then you would have a gamma 5 gamma, and here you would have a gamma 5 gamma. What I'm saying is that the gamma 5 gamma term, if here I put a gamma 5, this is 0. You can check that it is 0. Because this is a 0 form and this is a 1 form. So you have the opposite statistics that you have with two 1 forms. This is 0 with the gamma 5, but it is non-zero, and in fact, this sums to this when you have a single gamma. Well, these are the Majorana spinors. You can check it easily, in the sense that you have psi bar gamma 5 gamma A chi. If these are two 1 forms, this would be equal to minus chi gamma 5 gamma A psi. But if these are, okay, if these were two one-forms, Majorana one-forms, you would have a minus sign here. And this is why, for example, chi cannot be equal to psi, because then it would disappear. But if this is a zero form and this is a one form, then you have the opposite statistic and you have a plus sign. If this is a zero form, like in this case. But then you see that if you put a gamma 5 here and a gamma 5 here, then according to this has a minus sign, this has a plus sign to cancel. Then you have to have a single gamma, not gamma 5 gamma 6. And this is why I'm selecting this part here, because this gamma 5 kills this gamma 5. So that's it. Okay. Just to say, now that I'm substituting this with this part of the gamma loop. Okay. And this is what I do. We're doing it here. And so this sum becomes 2 times, in fact, I epsilon AR SD epsilon gamma d psi R SD. The sum. This plus this, the sum, I just substituted this inside. This I can rewrite in this way, minus 2i Rs epsilon gamma d psi VA epsilon Rs dA. I put the epsilon at the end, I change the place of this A, and this takes a minus sign, and the rest is unchanged. This is a 2 form, I can commute it everywhere. Okay. And now you recognize that this term exactly cancels the first term. The first term, that is this one, that is this one, that is this one. These 2 terms cancel, provided alpha is equal to I. So this term cancels with the 2 terms that we have underlined, with this and this, provided alpha is equal to I. And we took care of 1, 2, 3 terms. Now we are left with this and this. And it will be the last part of the last part of the proof. Is it clear? So the third and the fourth and the fifth term, let's write them. Epsilon bar, gamma phi, gamma A psi, psi bar, gamma A psi. The third term, then we have plus 2 times epsilon bar, gamma A psi, psi bar, gamma phi, gamma A d psi. These are the remaining 2 terms in the variation. I just rewrote them. I put 2i in as a factor.
Minus.
This is an I now. Here there was a minus, you are saying.
There's a relative minus sign between the 2 terms.
There should be a relative minus sign between the 2 terms. It looks like it, yes. Minus 4i. Let's see if it is in the same order. No, it is not. This is a 1 form. This 1 form has been commuted to a 1, 2, 3 form. So a 1 form with a 3 form gets minus sign. So this is a plus. Okay, so let's check whether this is 0. My claim is that it is 0. So we have to work a little bit. Okay, so it is the first term, epsilon, gamma phi, gamma A, c, c bar, gamma A psi. This is bilinear. This is everything is a okay. This is a fourfold, and then we have this one. Now, here, for the first time, we need the so-called fields identity. We will need it only once. You see this psi bar. If you put spinor indices, this is a matrix in spinor space, right? It is a matrix in spinor space. It is a two-form with matrix indices in spinor space. So it is, since it is a matrix in spinor space, it has these two indices, alpha and beta, that are spinor indices. I can decompose it on a basis, on the complete basis of gamma matrices. These are the complete basis for matrices in spinor space, the gamma matrix, the 16 gamma matrices. And so this means that it can be written in the following form, which is what is called a fields identity. Now, this holds for any product of spinors, where here you have spinor and here you have the bar on the spinor. And it goes like this. I write it in general for any product of spinors. In this case, I consider spinor one-fourths. This is for any lambda chi spinor one-fourths. Majorana. Majorana spinors. So this is 1/4, and you can flip it, chi bar lambda plus, and this is proportional to the matrix 1, the identity, plus you have something proportional to the matrix gamma phi, which is simply chi bar gamma phi lambda, minus you have something proportional to, no, plus something proportional to gamma A, which is chi bar gamma A lambda, minus, here with a minus sign, chi bar gamma A gamma phi lambda proportional to gamma A gamma phi, and finally we have the last piece, which is minus 1/2 chi bar gamma AB lambda proportional to gamma AB. This is it. This is the fields identity for spinors in 4 dimensions. And these, you see, are a complete basis of 4x4 gamma matrices. Any matrix in spinor space can be always expanded. This particular matrix is expanded in this way. You can check it. To check it, it is not difficult to check it. What you do, you just take the trace. You know that the gamma matrices are trace orthogonal in the sense that if I call gamma A trace over gamma A, gamma B is something proportional to delta B. But now, if you take all the 16 gamma matrices, you will find that they are orthogonal between each other when you trace them. For example, if you take gamma A and gamma A gamma phi, gamma B gamma phi, you trace their product, you find 0. Or gamma A with gamma CD, you trace the product, you find 0, and so on. So the Dirac matrices are satisfy this rule, gamma I, gamma J is proportional always to the delta ij, in the sense that they are orthogonal, and this is one of the 16 elements of the gamma matrix basis. Only when you multiply the gamma matrix by the same kind of gamma matrix, then you find something different from C.
Is this for 4 dimensions or In case of high
No,
dimension,
this holds always. This holds always. In particular, in 4 dimensions, you have 16 of them, and they are all trace orthogonal. Now, you can prove this thing by simply taking the trace of this matrix. You see, this is a matrix. You can take the trace of this matrix multiplied by one of the gammas. For example, let's take the trace of this matrix multiplied by the one matrix, the identity, which is part of the 16 gamma matrices. Well, the identity is not a gamma matrix, but one of the 16 matrices of the Dirac basis. Okay, if you take the trace of this, obviously what you will get, if these are one forms, is chi bar lambda. Okay, because this is lambda A, lambda B. I have to trace these. I can interchange them because they are one forms and they are spinors, and what you get is chi bar lambda. Okay, but you can check that it is correct because here I have multiplied by identity, I multiplied by identity everywhere. I take the trace, I know that the trace, the identity is 4, and it gives me 4 divided by 4 chi bar lambda. But the trace of gamma phi is 0, the trace of gamma A is 0, the trace of gamma A gamma phi is 0, the trace of gamma A B is 0. So all of these disappear, and you have proven that indeed it gives this. Then you do the same thing with the gamma phi. Then this gives you chi bar gamma phi lambda when you take the trace, and indeed, if you multiply here by gamma phi, here you have the gamma phi, the gamma phi. Now, the gamma phi with gamma phi gives 1, and only this will contribute in the trace, all the other different traces, and so on and so forth. Is the way to prove this fifth identity.
but in higher dimensions, do you need maybe?
In higher dimensions, I need more matrices because the Dirac basis is bigger.
Yeah.
But in principle,
That's identity also.
in principle it holds also. It will be more complicated, but the same thing holds in higher dimensions. And it is the only formula you will ever need to produce all kinds of spinor rearrangements in any dimension. You do not need more. You just have to work the consequences of this.
So that's for all spinors, not only for Mariana.
This, in fact, is for all spinors, not only for Majorana. You're totally right. It will be, yes, you're right. Majorana just allows me to switch this. Is it true? Yes, it is true. Because I did not change. Yes, it is true. This is for all spinors. You're right. It is not only for Majoranas. Only if then I flip this, then I can flip spinors. Yes. I have 5 minutes.
You're already 25 all
Yeah,
the time.
you're right. But I'm at the end.
Okay.
I try to be quicker. You're right. Fine. Okay, so now, thanks to this identity, these two terms will be shown to vanish. These two terms will be shown to vanish now. Where were the two terms? Here. Here. Okay, then you recognize what happens if I take lambda and chi equal to the psi. If lambda and chi are equal to psi, this identity here becomes psi bar equal to 1/4, and then only two terms will contribute because psi bar psi, only this can be different from 0, psi bar gamma A psi, because this is 0, this is 0 when psi is equal to psi, and we said this one and the one with two indices. So we have this one plus, actually it will be minus 1/2 this one, psi bar gamma A psi, gamma A. These are the only two terms that appear in the expansion of this matrix if this is the Gravitino field, that is a spinor 1/4, and Majorana. The fact that it is Majorana means that this, and this cannot be there. Okay, so now I'm using this expansion. I plug it here, place of this. And the result is that I have this term plus, we come here using this. In that place, we have 2 epsilon gamma A of 1/4 gamma B C bar gamma B psi minus 1/8 gamma BC C bar gamma BC psi gamma 5 gamma A gamma 5 gamma A B psi. I just wrote the 2 terms epsilon gamma A, right? Epsilon gamma A, yes. Okay, this was the first one, and then the 2 terms, epsilon gamma A. Here I wrote the expansion. Here I wrote the expansion factor 1/4 minus 1/8, gamma 5, then I have gamma BC, gamma, okay.
They both see the deep side.
They both see the deep
First term.
side. They both see the deep side. They both see the deep side. Yes. Good. These are the 2 terms. They become this plus this. Now, here I add another little identity for gamma matrices that tells you that whenever you sandwich a 2 gamma matrix in this way, it gives you 0 in 4 dimensions. This is a peculiarity of 4 dimensions. It also can be proven by all this little algebra. And then you see that here you have a gamma A, gamma BC, gamma A. This can anti-commute here and it becomes gamma A, gamma BC, gamma A. So this term disappears. This term disappears. And if this term disappears, you are left with, and this is the final line, epsilon bar, gamma 5, gamma A, C, psi bar, gamma A psi, plus 1/2 epsilon bar, gamma A, gamma B, gamma 5, gamma A, deep C, and then psi bar gamma deep psi. That's it in its full glory. The final term, yes, right? This is not here anymore. Here you have gamma A, gamma B, C. Here there is the gamma 5. Here there is the gamma 5. I have the gamma 5, gamma A here, right? This gamma 5, gamma A, okay. In fact, I should have put these parentheses here because the gamma 5, gamma A multiplies here psi bar. So the 2 parentheses was here, so that you have this gamma 5, gamma A that appears here, the gamma 5, gamma A, and the gamma 5, gamma A. This is it. Because we have again this thing here that gamma 5, gamma A, you can check that when you contract this index with this index, this gives 2 times gamma B, gamma 5. And so here you can replace it with 2 times gamma B, gamma 5, and if you do this, finally, you recognize that this and this cancel. The 2 goes with the 2 and gives you a factor of 1, and then you have gamma B, gamma 5, but here you have gamma 5, gamma B, as you can recall B if you wish. Here you have gamma 5, gamma B, here you have gamma B, gamma 5. The 2 things have a relative minus sign, so these 2 terms finally cancel. And this is the final line of the explicit proof in components of supersymmetry invariance of supergravity action. And I hope to convince you next time that there is a quicker way to prove it. Okay, let's see.